You're here because you want to master QA with a University of Cambridge graduate. Let's begin. Hi, I'm Brendan, and I've been helping students like you achieve their mastery over chemistry over the past 8 years, and I hope that you can learn something from me today. Before we begin, be sure to go into the link below so that you can download a free copy of my notes and use it to follow through our lesson today. So for QA, right, qualitative analysis, you must understand what the purpose of QA is for. Okay, QA is mainly used to identify the chemical components present in a sample, okay, rather than the quantity, right? So it's mainly used to identify, like in an unknown solution, right, what cations and what anions, what is inside this entire solution. You can have multiple cations and multiple anions, but with the correct test in your QA, right, you should be able to identify the specific cation or anion, right? So we are determining the presence or absence of specific elements or ions, compounds or functional groups, right? And we are mainly answering the question of what is in the sample and not really how much of a particular ion or functional group or whatever is inside the sample. So let's move on to our test for cations. For your test for cations, there are two tests that you have to memorize. Okay, you can react it with NaOH and you react it with NH3 aqueous. Alright, so you have these two reagents that you use to test for a cation. In general, right, you always want to add a little bit of the reagent first. For example, a little bit of sodium hydroxide first, and then you see if there's a reaction, and then after that you add it in excess to see if there's any furthermore reaction as well. Alright, same thing for ammonia. So each of our tests, right, will give a relevant observation depending on the cation. And I must say, this is something that you have to memorize. Yes, as a secondary school student, you have to memorize this entire table. This is going to affect your practical as well, okay? And you need to memorize everything so that you can easily come up with the answer and not need to like refer, or you don't need to like actively think on the spot, right? So for example, our copper 2 plus ions. If the solution is copper 2 plus ions, then when you add sodium hydroxide, you're going to get blue precipitate of copper 2 hydroxide. Okay, it's important to also identify the relevant components of our observations. For example, when we say a precipitate is formed, we need to know the identity of the precipitate. In this case, it is copper 2 hydroxide. No surprise, because it is a precipitation reaction. Copper 2 plus can react with OH minus to give a copper 2 hydroxide insoluble salt. Okay, and this precipitate is also insoluble in excess sodium hydroxide. This is also an important observation to note, again, because we will always add in excess later on as well. Okay, for our Fe2 plus, right, it's a green PPT, right, of iron 2 hydroxide, and this is insoluble in sodium hydroxide. For Fe3 plus, is red brown PPT of iron 3 hydroxide that is formed. Okay, and this precipitate is also insoluble in excess NaOH. A common observation is also that if you leave your FeOH2, okay, in the air long enough, right, it will actually oxidize, okay, or it will react with air basically. Okay, it will oxidize with oxygen in the air, okay, and it will slowly turn from green to red brown. So this is another observation that commonly comes out as well. Okay, next for our calcium 2 plus, okay, you'll give a white precipitate of calcium hydroxide, okay, and this is insoluble in excess sodium hydroxide. Your aluminium 3 plus, okay, is a white precipitate of aluminium hydroxide, okay, and this will actually dissolve in excess sodium hydroxide to give a color solution, right? So this is an important observation. Why does this do that? Okay, because it will actually form a complex. Okay, the aluminium hydroxide precipitate will form a complex. It will further react with OH minus, okay, to give that complex. Right, zinc 2 plus is the same thing. It will give a white precipitate of zinc hydroxide that is forming, and then the precipitate will dissolve in excess sodium hydroxide. Okay, if you realize, right, how do I remember these two are the ones that give this very specific observation? Because these are your actually part of your ZAP. Remember, ZAP is like your amphoteric oxides, right, that we cover in our acids, bases, and salts. Okay, and part of this community, okay, so your zinc and your aluminium hydroxide, these will both react with excess OH minus to give this complex. Alright, lastly, your ammonium ion, right? Remember, your ammonium ion can react with OH minus ions, okay, Okay, so upon heating, ammonia gas will be produced. Okay, and you must give the exact observation of ammonia gas. Okay, it's the effervescence of colorless pungent gas that will turn your moist red litmus paper blue. Okay, I cannot stress this enough on how exact your observation writing must be. Okay, so please go and memorize this. Now moving back up, right? So what happens if you test it with ammonia, aqueous ammonia, right? Aqueous ammonia is a weak alkali, so there's going to be a bit of differences in the observation for some of your cations. Okay, for example, your copper 2 plus, you'll still give this blue precipitate of copper 2 hydroxide, again because ammonia still is a weak alkali, it will give OH minus ions. But if you add it in excess, your blue precipitate will actually dissolve in excess ammonia to give dark blue solution. And this dark blue solution is a complex as well, right? You don't need to know the formula of this complex, but complex is still produced. Then your green PPT of iron 2 hydroxide is formed when you add ammonia to iron 2 plus. So same thing, it's still insoluble in excess ammonia. Fe3 plus is still red brown PPT, right? Of FeOH3, okay, and still insoluble in excess NH3. Your calcium 2 plus on the other hand has no reaction. Okay, why does there no visible reaction? Actually, there's a bit of reaction, but you just don't see it. Okay, because your calcium 2 plus ions is going to react with OH minus ions to give calcium hydroxide. But the concentration of OH minus is very low because it's a weak alkali, remember? Okay, and your calcium hydroxide is partially soluble. Remember, your calcium hydroxide is partially soluble in water actually. Okay, so you produce only a little bit of this precipitate, but it's just going to be still dissolved anyway, so it doesn't really come out as a precipitate. Next, your aluminium, right? Al3 plus, we'll give a white PPT of AlOH3 first, okay, but this precipitate is now insoluble in excess. This is the key difference, it's insoluble in excess NH3 compared to your zinc. Zinc, right, will still get this white PPT, but this zinc hydroxide will still dissolve in excess NH3 to give a color solution. Again, because you will form a complex over here, right? And your ammonium ion is not going to react with aqueous ammonia. Next up, we talk about our test for anions. So test for anions, right, is more specific in the sense that each anion, right, will have its own specific test. Okay, so in general, when you have a solution, right, and you want to test and find out the anion, you have to kind of do the anion test in sequence. I've actually listed it out in sequence over here from top to bottom, right? So you usually want to do the first test first, then the second test, then the third test, okay? Because in general, the test above is easier to do as well, okay? So first, for carbonate anions, right, you want to add hydrochloric acid and then you bubble the gas through lime water, okay? So you generally just add an acid and you want to see if there's acid and carbonate reaction. If there is, and you see effervescence, alright, then you will bubble the gas through lime water to confirm, okay, that this effervescence of colorless and odorless gas that forms, okay, when bubbled through lime water, can give a white precipitate. So we confirm the gas is carbon dioxide. Okay, you have to know, okay, what lime water is. Lime water is calcium hydroxide, and you have to know that the precipitate that is formed, this white precipitate formed when carbon dioxide is bubbled through lime water, is actually calcium carbonate. Okay, you must also know the ionic equations for such reactions as well. When acid reacts with a carbonate, in general, it's just a H plus reacting with CO3 2 minus if it's a soluble carbonate. Okay, and it will give you carbon dioxide gas and water. Right? Your sulfate anion, on the other hand, right, you will test it by adding dilute nitric acid first, followed by aqueous barium nitrate. Okay, a lot of our anion tests, right, you want to always add an acid first, or you add acidified something, right? The reason why we add an acid first, right? Okay, this is very important. The reason we add acid first, okay, you can take this down, okay, it's because we always want to test for a carbonate anion first. Okay, if you do not test for carbonate anion, what's going to happen later on is that even though you might get a white precipitate or a precipitate in your observation, right, you still have no clue if it's a carbonate anion or anion that you're testing. Okay, I'll give you an example, right? So for sulfate anion, you're going to add barium nitrate. Okay, why do we use barium nitrate? Because you want to do a precipitation reaction. Barium and sulfate ions, right, they can react and give an insoluble barium sulfate. Okay, so it's a very easy test. If you didn't test for carbonate, right, and you got this white precipitate, I'll tell you this, right, your barium right, could also react with carbonate ion the same way in a precipitation reaction to give barium carbonate. This is a insoluble salt as well, and this is white as well. Okay, so the only way to test for your carbonate, right, or to eliminate the whole presence of it, right, and eliminate that option, is to add dilute nitric acid first. Okay, same thing in our chloride test. We want to add dilute nitric acid first, same reason, and then we add aqueous silver nitrate. Okay, we add silver nitrate because Ag+, the silver ion, can react with chloride ions to give silver chloride as a white precipitate. Again, very easy precipitation reaction. Right, your iodide ions, right, you also use the same reagent. Okay, the way to tell the difference is that your silver will react with iodide ions to give silver iodide. Silver iodide is a yellow precipitate, right, versus silver chloride is a white precipitate. So do remember these colors. Okay, lastly, for nitrate anion test is the most difficult, okay, because you need to heat. Okay, so you add aqueous sodium hydroxide and then aluminium foil, and then you warm the mixture. Okay, this is the only reaction that you remember will have aluminium foil. Okay, so from this reaction you will get colorless pungent ammonia gas that will turn moist red litmus paper blue. Okay, the ionic equation for this reaction is simply just ammonium ion reacting with OH- to give ammonia gas. Lastly, you need to know all your tests for gases. I kind of touched on some of these beforehand already, okay, in our cation and our anion tests, right? But when you're writing observations, right, for any gas, right, it's very important to write the exact observation down to the detail, right? This shows how strong your chemistry knowledge is, right? So for example, your carbon dioxide, you don't just say, oh, carbon dioxide gas is produced. Remember, what do you see? What do you smell? Right? I see and smell, well, it's a colorless, odorless gas, right? And we know that when we bubble the gas through lime water, we get a white precipitate. Okay, so these are all very important tests. Okay, ammonia gas, we've also ran through this already, is a colorless, pungent gas that will turn your moist red litmus paper blue, right? Okay, so some of the gases we never ran through yet are our chlorine gas. Okay, this is a yellow-green, pungent gas. Okay, very bad, right? If you've gone to a swimming pool, you'll definitely smell a bit of chlorine before as well. It's quite pungent as well, especially if you go onto maybe like a cruise ship, right? And they have like an indoor swimming pool that is very pungent. Okay, and you will test this with a piece of moist blue litmus paper. Okay, your chlorine gas will turn your moist blue litmus paper red first because it's an acidic gas, and then it will bleach it. Okay, this is a very important info that you have to digest. Okay, your chlorine gas will actually bleach your moist blue litmus paper. Your hydrogen gas, okay, is a colorless, odorless gas as well, and it will extinguish a lighted splint with a pop sound. And then your oxygen gas, right, this is a colorless, odorless gas, and it will reignite a glowing splint. Okay, because oxygen gas is used in a combustion reaction. Okay, so you're actually like adding fuel in a way to the fire. Okay, and then lastly, okay, your sulfur dioxide. Okay, this is not very commonly tested. Okay, but your sulfur dioxide, right, is also a colorless, pungent gas. Okay, and if you bubble the gas through acidified potassium dichromate 6, right, very specific reagent, okay, you actually turn it from orange to green. Okay, you can also bubble it through acidified potassium manganate 7. Okay, it will turn it from purple to colorless, and that's how you determine it's a sulfur dioxide gas. If you enjoyed today's video, do remember to click the subscribe button so that you can enjoy more free content from us and improve your chemistry with us together. If you want to join my community of students to learn more secret formulas to acing chemistry, do check us out in the link below and sign up for a free trial class today.